So this is a reprisal of a talk that was given at the DNS OARC workshop in Los Angeles on October 12, 2014. We are cryptographers and network security researchers from Boston University and the Weizmann Institute in Israel. And this talk is about NSEC5, which is a proposal for provably preventing the zone enumeration problem in DNSSEC. What I'm going to do in this talk is walk through a variety of different constructions that were proposed and that exist today in DNSSEC. So NSEC, NSEC3, and then finally getting to NSEC5, explaining the security of each one of these solutions and sort of building up slowly to NSEC5. So even for those practitioners who are really familiar with NSEC and NSEC3, it might help to walk through this whole presentation with us because I'm going to point out exactly the different guarantees of NSEC and NSEC3 that we build on in order to get our security guarantees for NSEC5. So the zone enumeration problem in DNSSEC arises because of the issue of denial of existence. So what is denial of existence? So in DNS, there are two things that can happen. You can ask a query for a name, and the name can exist in the zone, and you'll get a response back telling you information about that name. Alternatively, you can ask a query for a name that doesn't exist in the zone, and then you'll get a response back saying that no such name exists in the zone. So that latter case is the denial of existence case, and there's lots of different ways to deal with this. RFC 4470 recommends online signing. Alternatively, there's the NSEC solution, and alternatively to that, there's NSEC3. Now, NSEC and NSEC3 are known to be vulnerable to zone enumeration. Zone enumeration is when an attacker makes a small number of queries to a name server without knowing what names are present in the zone, and then uses the information in those online queries to learn all the names that are present in the zone, to enumerate all the names in the zone. Usually this zone enumeration takes place using offline dictionary attacks. And these attacks are not just theoretical, they've been demonstrated on live zones. And this is actually why we introduced NSEC5. NSEC5 is a construction that can prevent the zone enumeration problem. It looks just like NSEC3, in fact. So for those who know what NSEC3 is, what we're doing in NSEC5, NSEC3 uses a hash function. What NSEC5 does is it replaces the hash function used in NSEC3 with a special hash based on RSA, and here you can see the hash. The idea is that this hash has a secret key, and because the attacker doesn't know the secret key, he cannot do zone enumeration attacks offline. So we can prove that NSEC5 prevents zone enumeration, and we can also prove that NSEC5 maintains the integrity of the zone. It doesn't compromise any of the security of DNSSEC. And in particular, this is true even if the hash key right here that we use in NSEC5 is leaked or exposed. Even if this hash key is leaked or exposed, we still don't lose any of the integrity or authenticity of the zone. All that happens is we lose the protection of NSEC5 against zone enumeration. So effectively, we roll back to NSEC3 type of security guarantees when this hash key is leaked. So we hope that NSEC5 gets implemented, and if this is of interest to you, please do get in touch with us. We are starting on this project right now. Okay, so let's look at how denial of existence works using the online signing solution. Okay, so here's our name server, and here's our resolver over here, and here's our zone file. Our zone file contains the following three names, a.com, c.com, and z.com, and it also has a DNS key. So denial of existence happens when a query comes in for a name that's not present in the zone. So you can see that q.com is not present in this zone because we only have a, c, and z. And so this name server has to respond with no such name exists. So here's how he's going to do it. We're going to give him the secret zone signing key that corresponds to this public verification key. What he's going to do is he's going to take the zone signing key and he's going to sign a response that says q.com NX domain. This name does not exist. And that's going to be sent back to the resolver, who will then be able to use the DNS key here that it has to verify the signature on this message and know that q.com doesn't exist. Okay, so that's roughly the online signing solution oversimplified in RFC 4470. So this solution provides integrity. No man in the middle can forge these sorts of responses if he doesn't know the secret zone signing key. And so that provides us with great guarantees that we don't have with DNS. But there is some problems with this solution that are important to keep in mind, and those are the fact that we've given secret cryptographic material, the zone signing key, to all of the name servers that have to work in this zone. Since every name server will have to answer queries that do not exist in the zone, each name server is going to need to have this secret key, and so if the secret key is lost, we can have some problems. So what happens if this name server is compromised? This name server now holds the secret zone signing key, and they can start signing bogus responses for things that aren't true. So for example, they can claim queries that do exist don't exist, they can give bogus responses, and so on. And so exposing this zone signing key to every one of the name servers can be considered a security issue. So I'm going to call that not tolerating a bad name server, or not tolerating a corrupted name server. This online signing solution in RFC 4470 does not withstand a corrupted name server, because it could leak the zone signing key and the adversary could then construct bogus responses. Okay, so fortunately we have a solution that doesn't suffer, and that's NSEC. So NSEC is a pre-computed denial of existence. So what happens here is that we have this authoritative name server who has the zone files, and now he's also given an extra set of records. These records are called NSEC records. So let's look at how NSEC records are constructed. So to construct an NSEC record, what you do is you take the zone file, you take all the names in the zone, and you sort them in some sort of order, so alphabetical order usually. And then you take every adjacent pair of records, so here's a.com and c.com, and then you sign that pair of records, okay, so using the secret zone signing key. Then the next pair is c.com and z.com, signed with the zone signing key, and finally we wrap around z.com, wrapping all the way around to a.com, signed with the zone signing key. Now, the trusted authority for this zone would have done all this signing, and then it would deliver these signed records to the name servers without the zone signing key. So the zone signing key is not stored at the name server anymore. All he gets are these NSEC records that are pre-computed for him. So now let's see how you answer a query. So here comes the query for q.com that doesn't exist in our zone. So this name server now, what he's going to do is he's going to look for the NSEC record that surrounds this query q. So here we have q.com. Q is after C and before Z, and so what this guy is going to do is deliver the NSEC record whose endpoints are around this query in alphabetical order. Okay, so Q falls between C and Z, and that's getting returned to the name server, to the resolver. So these NSEC records basically attest that there's no existing names between the pair of names on the endpoints of the NSEC record, and that's why this is the appropriate NSEC record to respond to this query q.com. So let's try to understand why NSEC maintains integrity. Okay, so integrity for us is going to be that an adversary here, let's say a man in the middle, cannot convince us that a name that really does exist in the zone, like a.com, here you see the query was for a.com, and a.com really does exist. So this guy cannot convince us that the query for a name that really does exist in the zone actually does not exist in the zone. Okay, so this adversary doesn't have access to the zone signing key. All he can do is observe messages that were sent on the network. So in particular, you could imagine that these NSEC records were sent out in the past in response to other queries that were made by legitimate parties or other parties. But there's really nothing that this guy can do in order to convince the resolver that a.com exists. So basically, all he can do is try to replay NSEC records that he might have learned. So let's imagine he collected all the NSEC records for the zone. And now he's going to pick one in order to replay to the resolver. So here we have the record a.com and c.com. Now that's not going to work because a.com doesn't fall between a and c, it actually is a. So this NSEC record won't work. This record here, c and z, well a doesn't fall between c and z, so this record's not going to work. And then let's look at this record. Again, it's not going to work because a.com is an endpoint here, and what we need to do is find an NSEC record that surrounds a.com, but is not an endpoint. So neither does this NSEC record work. So any of the NSEC records that he's collected could not be replayed and would be of no use to him, and therefore there's really nothing he can do in terms of convincing us that a.com doesn't exist when it really does. And that's the reason that we have integrity with NSEC, even though it's a pre-computed denial of existence solution. And it also has this really nice property that even if the adversary is actually the name server itself, even if this name server is corrupted, it still can't violate integrity because, again, all he's doing is replaying existing NSEC records, and that's not going to help him at all, just like we argued for the man-in-the-middle attacker. Same attack doesn't work. Okay, so the big idea here is that we do no longer have the zone signing key living at this resolver, so we no longer have to worry about compromises at this resolver. This resolver, his powers are just like a man in the middle, and we basically proved that a man in the middle cannot violate integrity with the argument before, or we argued. Okay, so so we have this great solution, NSEC, that provides integrity even if the name server itself is corrupted. But actually, NSEC introduced a new issue, which is called zone enumeration. So let's look at the zone enumeration issue. So here we have a zone with n names, where n is 3, And now this guy here, the resolver, is going to try to learn all of the names in this zone without any prior information. So let's see how he does it. So he picks a random name. Let's say he picks b.com. And in picking b.com, he'd get this NSEC record back. You can see that b falls between a and c, and so this is the appropriate NSEC record. And now our zone enumeration adversary has learned something very useful. He's learned that a.com and c.com are present in this zone. So now he wants to know what else is present. You know that c.com is present, so the next thing he'll ask for is d.com. And asking for d.com would get him back this record here, because d falls between c and z. And now he's already learned that z.com is present in this zone, because here it is in this NSEC record. And so you can continue this process, and in fact this guy's already done. He's enumerated every single name in the zone using exactly 3 queries. So this is kind of an interesting situation, because in DNS and in online signing solution, in receiving a response to denial of existence actually doesn't reveal any information about other names that are in the zone. But NSEC actually does. And using NSEC, you can actually learn all the names that are present in the zone, which is something that wasn't even an issue with DNS, like insecure DNS, and is also not an issue with online signing. At this point, you might ask why zone enumeration is an issue. So it was enough of an issue to actually introduce NSEC5. And let me just give some of the reasons that have been mentioned. So enumerated zone can expose device names. With those device names, you can then sort of survey a network and use that to launch other attacks. Alternatively, it could be a source of probable email addresses for spam, and this would compromise a registrar's attitude toward consumer protection. Alternatively, you can use the information in the zone file as a key for whois queries that can reveal registry data that violates data protection laws. And finally, it conflicts with registry's legal rights. So the actual registry database, the zone file, is a business asset, and its compilation is protected under copyright or database rights. And so leaking this all through zone enumeration violates the legal rights of the registry itself. So these are all the reasons that we found online, to talk about why zone enumeration is an issue. And the bottom line is it was enough of an issue to drive the creation of a new solution, which is called NSEC5. So let's have a look at NSEC5. Okay, so how do you compute NSEC5 records? So right now, we're going to talk about what the trusted authority for the zone, the authority who actually holds the zone signing key, does ahead of time in order to pre-compute the NSEC5 records. So what he's going to do is he's going to take all the names in the zone, and then he's going to compute a hash on these names. So for example, SHA-256 computed on every name in the zone, and that's going to give us a bunch of hash values. The next thing that's going to happen is these hash values will be sorted. So 2 comes before A comes before D. So now we've sorted these hash values. And finally, just like in NSEC itself, we're going to sign every pair of these records. So we're going to take the first pair of records and sign them using the secret zone signing key. So here we have 2 and A signed by the secret zone signing key. That's the first NSEC5 record. The next NSEC5 record is the next pair, this pair here. And then finally we have another NSEC record for the wraparound from D back up to here. And all of this are signed with the secret zone signing key. So this is done ahead of time, offline, by some trusted authority that actually has the secret key. And again, we're back to looking at how you answer queries with NSEC5, and remember that we have our name server here that's given these NSEC5 records, but not given the zone signing key at all. Okay, so this guy does not hold the zone signing key, he just has these pre-computed records. So how does he respond to a query for a name that doesn't exist? So our name server asks for resolver asks for q.com, and q.com is not present in this zone. So what the name server is going to do is he's going to compute the hash of q.com. So here's the hash, that's this value starting with C. And then just like with NSEC, he's going to find the NSEC5 record that this hash value falls between. So C falls between A and D. You can see that this hash value falls between these two hash values. And so the appropriate NSEC5 record to return is this NSEC5 record here. Okay? Now the name server, the resolver, can therefore verify that this is the correct NSEC5 record by first computing the hash of his query, which he can do because it's just a SHA-256 hash. Checking that the number that he gets falls between these two numbers, so this number here should fall between these two numbers, and then doing the verification of the signature on the NSEC5 record using the public key for the zone. So NSEC5 provides integrity for the same reasons that NSEC does. The reason is that an adversary will not find an appropriate NSEC5 record to replay. Because he does not have the zone signing key, he can only replay NSEC5 records. and given that the NSEC3 records are formed in such a way that the query will either be the endpoint of one of the records or not fall between any of the records, there's no valid NSEC3 record that he can replay. Okay? So integrity is protected for the same reason as with NSEC. Similarly, this tolerates a bad name server because we do not give the secret zone signing key to this name server. So the power of the name server is about the same as the man in the middle. And now the question is, does it actually protect against zone enumeration? Okay, so here's our zone enumerator, and he wants to learn all the names in the zone without actually having any prior information about what's in this zone. So from the previous query that we saw, which delivered the middle NSEC3 record, he learned already two names. He learned, sorry, not names, but hash values. He learned two hash values. He learned this A hash value, and he learned the hash value starting with D. So he wants to now learn some more hash values. So he'll ask another query for, let's say, r.com. The name server will compute the hash of r.com and get a new hash value which starts with 3. And now he's going to need to look for the right NSEC3 record, which will be the first NSEC3 record, as we can see, because 3 is after 2 but before A. And now you can see that this NSEC3 record, which goes back to the resolver, gives him a new piece of information, a new hash value, this hash value starting with 2. And again, as we showed before, this process can continue and allow the zone enumerator to learn all the hash values in the zone. So now the question is, does this mean that we have a zone enumeration problem? So what the zone enumerator in this case has learned is all of the hash values in the zone, but he hasn't actually learned all the names in the zone like he was able to do with NSEC3, with NSEC itself. And so now let's actually have a look and see what this zone enumerator can do with the information that he's learned here from these hash values that he's collected. So the second part of the zone enumeration attack is actually an offline attack where he takes the information that he learned by making queries to the name server, so these hash values, and he uses an offline dictionary attack to reverse them and learn the actual names in the zone. So how does this work? So in an offline dictionary attack, the attacker starts with a dictionary of plausible names for the zone. So here's my plausible dictionary, which is a.com, b.com, and so on. Then he's going to take every name in his dictionary and compute the hash of that name. So now he has a bunch of hash values, as we can see here. And now what he's going to do is he's going to take the hash values that he's learned from his dictionary and see if any of them match the hash values that he learned from the queries he asked earlier. So you can see that this hash value here, A, starting in A, matches a hash that he learned from asking queries. And he knows now that this hash value maps to a.com because it's from his dictionary and he computed this hash value on his own. He can continue this process here, this hash value starting in D. He now knows it corresponds to z.com. Right? The reason for that is because his dictionary contains z.com, and he computed the hash of z.com and found a match. And this process can continue. So here he learns c.com. And actually, I just want to note that I've oversimplified this. There's actually salt values that are included in with the hash, and it's one salt for the entire zone. There's multiple hash iterations to slow down the adversary and so on. But all of this sort of not the focus of my talk. I just want to mention that zone enumeration has been demonstrated. In fact, in 2014, this group from Germany reversed 64% of the NSEC hashes in the .com TLD in just 4.5 days using a graphics processing unit. So these attacks have been demonstrated, and this is why we introduced NSEC5. So what is the reason? Before we go into NSEC5, let's just look at the fundamental issue here and explaining why zone enumeration is possible with NSEC3. So in NSEC3, when the resolver asks a query for something, the name server will compute the hash of the query, find the matching NSEC3 record, right? So this hash value starting in C falls between A and D, and so this is the correct NSEC3 record. And now what our zone enumerator does is he takes the hash values that he's learned from the NSEC record. So you can see this A hash value and this hash value starting with D, and he runs off and does this offline dictionary attack, whatever technique that he happens to use. So the fundamental issue here is that our adversary has the ability to do offline dictionary attacks because he knows how to compute hashes. An offline dictionary attack depends on the ability to compute hashes, and since our adversary knows how to compute hashes, he has an offline dictionary attack available to him. What we're going to do in NSEC5 is to eliminate these offline dictionary attacks. We're going to introduce a keyed hash. Okay, so what we're going to do is we're going to give the name server a secret key that we call the non-signing key, NSK. And I want to emphasize that this key is different from the zone signing key. This key is not used to sign records, it's just used to do hashing. Okay, so what's going to happen is now when the query comes in, the name server is going to compute this keyed hash using this non-signing key to get this value, find a matching NSEC5 record. So you can see the idea of matching is just like in NSEC3. We can see this hash value starting in 7 falls between these two hash values starting in 3 and 8, and therefore this NSEC5 record corresponds to the hash of the query. And then he's going to send that back to the resolver. Okay, so the resolver now, if this was NSEC3, would have these two hash values, right, that he would then run off and try to crack using his offline dictionary attacks. Okay. But this is where the key comes in. Now, the reason that we have a key here is to actually prevent the offline dictionary attack. Our zone enumerator can no longer compute hashes offline because he doesn't have the secret NSK. And since he doesn't have the secret NSK, his dictionary attacks are not going to give him anything because he can't even compute hashes in order to compute the hashes of what's in his dictionary. Okay, so the bottom line is all the offline dictionary attacks that we see go away because the hash is keyed, and so the adversary can't compute hashes offline to do the dictionary attack. Okay, so that's the rough idea behind NSEC5. And now let me go into the details of how exactly NSEC5 works. Okay, so the first thing we need to do is understand how the trusted authority for this zone, who actually holds the secret zone signing key, can compute the NSEC5 records. Okay, so as before, we start with our records in our zone file, and then we hash them. But now instead of hashing them just with a normal hash like SHA-256, we're going to use a special hash, which is keyed with this secret non-signing key. So what's our hash? Our hash first takes the query and computes a deterministic RSA signature on this. So for those who are familiar with the cryptographic details, this is full domain hash schema of RSA. But the bottom line is we take the secret key, we compute an RSA signature on the query, and then we hash that signature. And the output of that is going to be our hash value. Okay, so for every name in the zone, we're going to first sign it with RSA and then hash it using some sort of cryptographic hash function like SHA-256. So now we have a bunch of hash values, and then we do exactly what we did in NSEC3. We sort the hash values in alphabetical order. So here we can see that 3 comes before 8, which comes before 9. So these are sorted hash values. And then we're going to take the zone signing key, right? This is a different key than the key that was used for hashing. This is the signing key. And we're going to sign NSEC5 records. So we take every pair of records that are next to each other and we sign them to get these 3 NSEC5 records. So as you can see, we have the first pair signed, the second pair signed, and then we wrap around from the hash value starting with 9 to the hash value starting with 3. And these are our NSEC5 records. Okay, so this process involves two types of keys. The non-signing key, which is used for hashing, and the zone signing key, which is used to actually sign the records, just like in traditional NSEC, NSEC3. Okay. Just like before, the trusted authority for the zone will give the name servers these NSEC5 records, in addition to the zone file. But now we have to also give him this secret non-signing key. Okay, so this is different from the zone signing key. Remember that this is only the key that's used for hashing, not the key that's used for signing records. Okay, so now when a query comes in, right, so here's a query for q.com, which is not present in the zone. Our name server has to figure out which NSEC5 record it's going to give back to the resolver. So the first thing it's going to do is it's going to take the query, and it needs to compute this so-called hash of this query. So the first thing he's going to do is compute the RSA signature on the query. That'll give him this value here. Then he's going to hash that value, right? So we'll get this hash value starting in 7. And then he's going to return the correct NSEC5 record. And this is, again, the usual thing that we do. We look for the record that has 2 values that surround the value of the hash here. So 7 comes between 3 and 8. And so this is the matching NSEC5 record for the output of this hash function here. Okay? So that's NSEC5. The idea is that it's just like NSEC3, except instead of using a regular hash function, we use this fancy hash function, which first involves computing a signature using the NSK, the secret NSK, and then hashing the result, and then finding the matching NSEC5 record. So that's the job of the name server, computing this online signature. And at this point, you should be very confused because it's not at all clear how the resolver should be able to verify this NSEC5 record. So how does this work? So the problem is that this NSEC5 record, he needs to check that q.com really falls between the 2 values in the NSEC5 record, but he has no idea how to compute the hash because he doesn't actually have the secret key. So what should he do? So this is why we need to take this value over here, this RSA signature value here, we're going to call it a proof, and we're going to have the name server actually tell the resolver what the output of the hash was. Since the resolver can't compute the hash itself, he's just going to have the name server tell him. And so in addition to the NSEC5 record, we're also going to include this proof record, which contains the RSA signature on the query using the secret non-signing key. Okay, so this value here is going to go over to the resolver as well. And now the resolver can use this value to make sure that the query actually falls between the two endpoints in the NSEC5 record. So he's going to take the hash of the value in the proof, that's that green value. He's going to end up with the number 7A89B, as before. And then he's going to verify that this hash value, 7A89B, falls between this hash value starting the first hash in the NSEC5 and the second hash in the NSEC5. And if that's correct, then he's going to be happy and everything works. But at this point, there's still a problem, right? So he's verified that the proof comes between the two values in the NSEC5 record, but how does he know that this query actually has anything to do with the proof? How does he check that the query actually matches the proof? Okay, and so this is the place where we actually start to use the fact that we've used RSA. So you'll remember that RSA is a signature algorithm that has a secret key that's used for signing and a public key that's used for verifying. And so if this resolver had the public key that corresponds to the secret NSK, he can then use this public key to do an RSA verification to check that this proof value is actually really an RSA signature on the query. Okay, so if you take the public key that corresponds to the secret NSK, do an RSA verification on the query and the proof. If the RSA verification succeeds, you know that the proof value was really the signature on the query, and that way you know that the proof and the query match. And then again, to check that the proof and the NSEC5 record match, you do the check of the hash of the proof, check that it falls within the two values in the NSEC5 record, and if it does, you're happy. Okay, so that's the NSEC5 in action. We have two verifications. The first verification is that the proof is actually the signature on the query, and the second verification is that the hash of the proof falls between the two values in the NSEC5 record. So I should just mention that this public non-signing key needs to be distributed to all of the resolvers, and this would be done using typical DNSSEC mechanisms for distributing keys. So it would be put in a DNS key record, which could be signed by the zone signing key, and distributed to the resolvers. And again, there are flags in the DNS keys that can indicate that this key is not to be used for zone signing, it's just to be used for hash verification. Okay. So we have this new kind of key that needs to be distributed, as well as a secret key that's stored at the resolver. Okay, so before we go into all the details, and I'm sure there are some issues and people wondering exactly how we deal with the fact that we've now given a secret key to the name server, and I'm going to talk about that in a second. I first want to talk about why NSEC5 prevents zone enumeration. So here's our zone enumerator, and normally in NSEC3 or NSEC, what he would do is he would take the values that he learned from the NSEC5 record, so you can see he learned these two hash values, 3CD91 and 8CB67. Take these two values, run off, and do an offline dictionary attack with them. Now the thing is, in NSEC5 actually, he can't do this offline dictionary attack because he can't even compute the hashes on his own. He doesn't have the non-signing key, and so he can't do this offline dictionary attack himself. And so that's why we stop the offline dictionary attack. Now, just as a reminder, this hash value here is the RSA signature on the query, then hashed by the SHA-1 hash. Okay, so at this point you might want to ask another question, which is that this resolver here was actually given the non-signing key, and maybe that actually will help him to do an offline dictionary attack. Maybe he can do RSA verifications to check that somehow that something corresponds to a value in his dictionary. Now it turns out that this is actually not possible either. So he has this RSA verification ability, because if you look at what he learns from the NSEC5 record, what he's learning in the NSEC5 record is the hash of signatures. And RSA verification works on proof values, which are RSA signatures, not on hashes of proof values, which is what's in this NSEC5 record. So the bottom line is that because the RSA verification algorithm just verifies proofs, and we don't actually have any proofs in the NSEC5 record, you can't use this verification algorithm to learn any extra information about the any extra information about the hash values that he learns from the NSEC5 records. So this was sort of an intuitive argument, and we have a formal argument that NSEC5 prevents zone enumerations in our paper, and in fact we even have In order to do this argument, we also have a cryptographic definition of what it means to have privacy in this setting, or what it means to prevent zone enumeration in this setting. So please see our paper for that. Okay, so the next question is, why does NSEC5 maintain integrity? So remember that integrity is the case where we have this adversary here that wants us to convince us that a name that does exist in the zone, like a.com, actually really doesn't exist in the zone. Okay, so he's going to try to convince us that a.com doesn't exist. So this adversary has the ability to listen on the network, and he can collect, let's say, NSEC5 records and start replaying them. Okay, but what he doesn't have is the secret non-signing key. So, for example, in this case, he could just have replayed some NSEC5 record that he saw from before. But the problem is he can't compute the correct proof on a.com, because remember that this proof value should be RSA signature using the non-signing key on a.com. Since this guy doesn't know the non-signing key, he can't compute this proof, and therefore his attack is going to fail, because the resolver, when he does his verification, will see that this proof value doesn't correspond to the actual query, and this response will be rejected. Okay, so for an adversary that doesn't have the non-signing key, we can see that he can't violate it. So here we come now to the big question. We've introduced this extra key, this non-signing key, and you might wonder, what happens if this non-signing key leaks, or what if this name server itself is compromised? What can he do with this non-signing key? Okay. So what I'm going to talk about right now is how NSEC5 behaves when the non-signing secret key becomes exposed, when it's no longer secret. And the spoiler is that the integrity is still preserved, but all we lose is security against zone enumeration. Okay, so I argue that NSEC5 maintains integrity even if the non-signing key is exposed. Okay, so let's see what happens. So here's our adversary, and he's somehow managed to get his hands on the secret non-signing key. Okay, so now when a query for a.com comes in, he wants to try to convince us that a.com doesn't exist. Now he has the secret non-signing key, so he can definitely compute the proof, right, because the proof is just the RSA signature on the query using the secret non-signing key, which he has, and so he gets the correct proof value here. But now what's going to happen is he's going to run into the exact same problem that he ran into when we were using NSEC3 and NSEC. Okay, so he has this hash value. Now what he needs to do is he needs to find an NSEC5 record, to replay some NSEC5 record that the hash of the proof actually falls between. So here's the hash of the proof. It's this value starting in 9, right? And this is the value for a.com. So now he needs to find the right NSEC5 record to replay. So let's go through each one of them. So this first NSEC5 record won't work because 9 does not fall between 3 and 8. The next NSEC5 record won't work because this 9AE3E hash value is actually part of the NSEC5 record, so that won't work. The third NSEC5 record won't work because this is another endpoint of the NSEC5 record. 9AE3E appears in the NSEC5 record, so that's not going to work. And the bottom line is, these NSEC5 records are constructed in such a way that there's no record that the adversary could replay in order to convince the resolver that a.com doesn't exist when it really does. Okay, so what this comes down to is the fact that because of the way we form the NSEC5 records and the fact that the adversary does not have the zone signing key, he cannot replay or construct an NSEC5 record that will actually match a.com as the correct value. So, and this is true even if the adversary is the name server itself. Even if this name server gets compromised or decides to misbehave, he can't deliver bogus responses because the NSEC5 records, he doesn't have the ability to sign NSEC5 records, he doesn't have the zone signing key, and so he can't replay an NSEC5 record that will convince the resolver, that a.com doesn't exist in the zone. This is exactly why NSEC and NSEC3 were secure against attacks on integrity. So NSEC5 tolerates a misbehaving name server, and in fact, NSEC5, when the non-signing key is lost, actually looks just like NSEC3. We don't have any compromises on integrity, but all we get is we have a vulnerability to zone enumeration. So we basically have the security guarantees of NSEC3. Instead of having protection against zone enumeration, we're now stuck with zone enumeration because the non-signing key was exposed. But we don't have any attacks on integrity. And I just want to make a note that if the non-signing key is exposed, let's say that the name server gets hacked and the non-signing key is exposed, the adversary that hacked the name server has access to the zone file anyway, so it's not really of much use to him to expose the non-signing key. Okay. So this is really the big difference between NSEC5 and online signing. In online signing, if the name server is compromised, it can start saying bogus things. It can deliver NX domains for names that are actually present. It can sign bogus A records. It can do all sorts of things like that. Because the zone signing key really protects the integrity of the zone, and if the name server is hacked and that key is leaked, all of the integrity is lost. On the other hand, in NSEC5, if the name server is attacked and the non-signing key is leaked, the NSK is leaked, all that happens is we have a vulnerability to zone enumeration. We don't have any attacks on integrity. So all of this that I've just talked about is proved in our paper, which you can find here. Some of us are cryptographers, and so there are cryptographic proofs in the paper proving all of these claims. Okay, so let me finish with a few practical issues. So what's the difference between NSEC5 and NSEC3? So the most obvious difference is that in NSEC5, the name server has to do one online RSA signature for every query that it gets in order to construct this proof value. And I would mention that on the resolver side, actually, there's not much of an increase in overhead, because today NSEC3 specs even recommend that the hashing done in NSEC3 should be, the number of hash iterations in NSEC3 should be equivalent to one RSA verification. And in fact, in our scheme, we do exactly one additional RSA verification at the resolver. So this is not an extra overhead at the resolver over what's recommended at NSEC3. But it is definitely an additional overhead at the name server, having to do one RSA signature per query. But actually, we can prove that this online signature is necessary if we want to prevent zone enumeration. So we have this theorem that says that any denial of existence scheme that both prevents zone enumeration and provides integrity, even if the name server is attacked or hacked, even if the key material in the name server is exposed, that requires name servers to compute one public key signature for every negative response that it gets. So in some sense, our solution here is actually optimal, because our theorem here proves that we need one signature per query, and that's all we actually require in NSEC5. And this theorem also explains why hash-based schemes like NSEC3 are vulnerable to zone enumeration and offline dictionary attacks. Okay, so this is the main place that you have to play with NSEC5. To get protection against zone enumerations, you need to have the name server do some extra work, which is to produce one RSA signature per query. The next place that we have to look at is key management. So in NSEC5, we have these NSKs. We have the public NSK, which is used for verification. And we also have the secret NSK. So distributing public keys in DNSSEC is a solved problem in a sense. We have the DNS key resource record that we can then use for the NSK. Now for the secret NSK, though, this is a bit more of an issue because it requires that we store cryptographic material at each name server. But I want to emphasize once again that this is not a high security key. It's not like the zone signing key. If the NSK is leaked, we do not have attacks on integrity of the network. All we have is attacks on zone enumeration. So the security of the secret NSK essentially has to be as secure as the zone file itself. If the adversary gets their hand on the zone file, if the adversary hack into a server and get their hands on the zone file, the NSK is actually of no use to them. The last place we have to pay is in the response size. So here's NSEC5 and NSEC3 records. Now we can see that they're actually exactly the same size. They both contain a signature. This lock here is the signature, which is signed by the zone signing key. And then, of course, the two hash values. So they have the same size. But in NSEC5, in addition to every NSEC5 record we have to send, we also have to send this proof value. So that's an additional 2048 bits. So that will increase the response size over NSEC3. But finally, I want to mention that there was this very clever optimization that was put together to deal with wildcards. So in practice, when we have a denial of existence query in practice, it's not true that we'll only return one NSEC3 record. We've oversimplified that in this presentation. Sometimes you can actually get up to 3 NSEC3 records. So there was a proposal to reduce the number of records that needs to be returned from 3 down to 2. All of these sorts of proposals can be incorporated into NSEC5 as well. And if you do that, you actually end up with that NSEC5 responses are only going to be 2048 bits longer than today's NSEC3 standards, which does not use the optimizations, which were developed after the standard already came out. So the bottom line is if we use some of the clever ideas that came out about NSEC3 after NSEC3 was standardized in our solution, we end up with responses that are only one RSA signature longer than the current unoptimized standard that's being used today. So the full details of our results are available on ePrint in this paper, whose link you can see here. And I just want to conclude with the records that we need for NSEC5. So first thing we need is this non-signing key, whose public version needs to be distributed to resolvers using the usual DNSSEC key delivery mechanisms. In addition to that, we have NSEC5 records, which look just like NSEC3 records. And in addition to that, we have this new proof record, which is basically an RSA signature that needs to be delivered with every NSEC5. So NSEC5 is an online signing solution, and I just want to be very, very clear on the differences between NSEC5 and the traditional online signing solution in RFC 4470. So if you look at the online signing solution, you can see that the online signing solution does not tolerate a bad name server. So if a name server misbehaves, in the online signing solution, it's given the secret zone signing key. And so if this name server misbehaves, he can start to sign all sorts of bogus responses. He can sign NX domains for names that actually exist. He can sign bogus A records and all sorts of things, whatever he wants. In contrast, in NSEC5, if the key material that we give the name server, which is this NSK, if the secret NSK is leaked in NSEC5, all that happens is we lose the privacy against zone enumeration. But we do not compromise the integrity of the zone. Even if the non-signing key is leaked, all an adversary can do is start to enumerate the zone, but they can't start signing bogus responses that say that records are present when they're not, or any other bogus information like that. So really, leaking the non-signing key in NSEC5 basically rolls us back to the guarantees of NSEC3. If you look at the last row in our table here, compare it to NSEC3, we can see that we get roughly the same security guarantees. And when we do keep the zone signing key secret, we actually do have protection against zone enumerations, and we can prove that this is true because breaking the hash function in NSEC5 is roughly as hard as breaking RSA. So that's the technical details of our NSEC5 proposal, and naturally there's lots of work to be done. So if this is of interest to you, please do get in touch with us. We're starting this project now, and we're very keen to get this implemented, standardized, and anything else. So thank you.